The pleasantries, my name is Pablo Rivas. I'm going to tell you about the big picture of the problem we're trying to solve. The problem is that we have different components of a larger project in which we're trying to detect both human trafficking and stolen car parts online in what is known as consumer-to-consumer platforms. The problem is largely relying on the type of input data that we have. And when we proposed this project to the National Science Foundation, they were eager to support it based on the social impact of it and also the intellectual merit of the project. Initially, we proposed to look into this from the two separate pieces, to look at it from analyzing images and also the text associated with it, understanding that the text analysis would be crucial to the success of this project. But soon, we also realized that dealing with images is also a huge problem, and we're then proposed to tackle it separately in self-supervised tasks and semi-supervised tasks. So what we're thinking is to have both an image encoder and a text encoder from these posts, and do a series of self-supervised tasks or no supervision at all, using either contrastive or reconstruction or some type of variational learning. And then after that, we will go through a process of fine-tuning with some weak supervision because of the absence of labels in this kind of data, that there is not very much available. And then do it with classification laws or some type of regression laws and align these latent spaces. The main issue with dealing with these is the cost. We don't have a ridiculous amount of GPU power, of course, and it can be very costly to train these models, such as a DALL-E or a GPT, to pick some of the most successful either image encoders or text encoders as well. So we're trying to avoid that. And to tell you a little bit more about the motivation behind this it has a lot to do with the type of data. If you look at a post on a consumer-to-consumer platform, it has a title, it has pictures, and it has a body of text. The title, however, may have numbers, letters, emojis, and the challenges associated with that is it can have typos, it can have slang, it can have secret codes. So if you're a criminal organization, they usually have intentional typos in the titles or some type of code to identify themselves. Pictures also have some challenges, that they have maybe zero or many of those, and they're completely uncontrolled conditions. And then the body has the same challenges as the title. In addition, it could be also some type of deceptive text or incomplete sentences. Variable length can be just one sentence or one telephone number, or it could be paragraphs and paragraphs of text. So this is very, very challenging, and you cannot just get rid of these slangs or typos, because they can be indicative or features that can tell us whether it's illicit activity or not. And in the same way, images, we cannot just get rid of certain pieces of it. We need to preserve it. And the other challenge with images in the case of human trafficking is that it can be graphic material, and we need to protect the researchers from being exposed to that material, especially if there are students involved in the project. So we need to focus on this piece of the images encoding quickly to provide the students with, or the team with representations that can be worked with without being exposed directly to them. So naturally, one of the main ideas that we were thinking of was, let's use a transformer. Everybody's using it, of course, but it has 86 million to 500,000 parameters, which is a lot of expense in compute. We could fine-tune it for sure. However, still in production, or when we release this to other law enforcement agencies, they will not be able to work with that effectively. The other great alternative will be bring your own latent, in which you bring your own piece of network and you can work around that, like a RESTnet or bring some other type of network that encodes, and then find your projections and train contrasting and align these projections. And that is great, except that it also is rather costly. It's a great deal rather costly. So we're shooting for something cheaper. Clip comes to mind as the alternative or the big picture of what we want to do in the end, in the sense that we want a text encoder and an image encoder. But again, we're trying to find these pieces that are really non-expensive to train. And so Clip's success is largely also based on the magnitude of its text encoder. I think it's a T5 and its image encoder as well. So what we're proposing is something cheap, and we call it a bare architecture. So let me explain these parts really quickly. The first piece of it is what we call a perceptual feature encoder. It uses, or its success, as we believe, it is based on a convolutional STM, it's rather forgotten element in machine learning and computer vision. And it is nice in the sense that it involves also the temporal aspect of color pictures. So you get the nice thing of having convolutional filters, but also using memory or long short-term memory, and deal with the temporal aspect of channels to learn better features and perceptual features. And so we do this back to back. In one of them, we just trying to reduce dimensions, and the other we just keep the same dimensions. And then after this, we have several of these pieces, but they are connected with the residual representations of the previous layers. And then we have at the end of this a bottleneck feature entanglement, or bottleneck that will yield us the latent representation we're looking for. And after this, it is the process of decoding and reconstruction using classic convolutional layers and upsampling, pretty much as the state-of-the-art does in ResNet and other architectures. During the training piece, we do the data augmentation, in which we vary the position of the angle and the position of the picture. And we use the standard reconstruction losses, a mean square error loss, or binary entropy losses, and standard learning rate and decay to stop training after no improvement for a while. There's also we obtain, we're measured in more than the 3 data sets that are here, but for the presentation, I'm showing this because this data is consistent. So it is scalable in the sense that the more data you have, you're gonna get a similar response in proportion to data set size is the training time. We also, this is real data from consumer to consumer website called Skip the Games, and we have shown here that the model can learn these spaces really well and find or grouping this the data in different categories that are very unique to the success of the project. So in summary, we presented something, some model that can find these representations. They're low dimensional. It uses fewer parameters. Depends on the size of your input. It can be from 5 million to 25 million parameters. And it hides the personal identifiers that protecting information of people, and it's really much greener than the others. And if you come to the poster, we'll also show experiments in many other data sets. Thank you.